Hi, everybody. Can you see my screen there?
Looks good.
Yep. I've just realized the chat's decided to close itself. Let me open that again and bring that to somewhere useful. And let's get as big as I can so that I've got some vague photos to talk to as we're doing this. Thank you for inviting me to come talk to everybody. I'm really excited by all of the stuff that I've seen from Chaos and what they've been doing. You guys are absolutely fantastic. So I'm really looking forward to seeing what you do in the coming years. So I'm an exoplanet scientist. And in my talk, I'm going to kind of hopefully give you a good idea about what I do, but I'm also going to talk about some of the things that I just love about planets, planetary atmospheres specifically. So I'm going to take you on a little bit of a journey, hopefully here. To do a journey properly, you kind of have to start at home. So we're going to start with our solar system. And the 8 planets that we have in our solar system are all really, really different from each other. And that's one of the biggest things that I want to get across here is that planets are really chaotic systems and they are different because of very tiny differences between those planets. And we'll look at some of those differences and what that means for those worlds. This is a scaled version of our solar system. So you've got the sun there, nice and giant in the middle. The sun is actually a fairly middle class star. It's middling temperature, middling size, middling color. It is orangey yellow. That's the middle color of stars. Stars go from a deep red up to a bright blue and white. So it's kind of in the middle of all of the types of stars that exist. And you can see our solar system down there. A nice big arrow pointing to Earth. We're going to have to zoom in a little bit to see our planets. You can see the curve of the sun still there, so you can work out what the radius of the sun is compared to these planets if you felt like it. But you can see Jupiter there is our giant. And although Saturn looks just as big as Jupiter here, it can actually fit inside it along with all of the other planets that you see there. And those little dwarf planets beyond Neptune, those tiny little planets down in the corner, that's our Pluto and Plutoids out in the Kuiper Belt. So our solar system is really diverse in its sizes, but one of the things that you'll notice here is that there's very small planets close to the star. So that's our Mercury, Venus, Earth, and Mars. And then we've got our giants, Jupiter, Saturn, our ice giants, which are also really large. They're 4 times the size of the Earth and about 20 times more heavy, more massive than the Earth. That's Uranus and Neptune there. And then again, we've got these very small objects out at the end. So that's really what we thought solar systems look like. This is our basis for hundreds of years of what solar systems look like. And exoplanets have really thrown a wrench in those works to try and us to understand, do we fit into our galaxy? Are we normal? Or is the solar system a little bit strange? The thing that I love the most, and I will always talk about, is atmospheres. Atmospheres are just what I study. I started studying them in my undergrad, and I went on in my master's and PhD to study them, getting further and further from the Earth each time. And the thing about the solar system atmospheres is they're all really different. And you can see just from these images, what I'm looking at specifically here are the clouds in the atmospheres of these planets. We've got beautiful Earth clouds made of water. We've got Venus's clouds, which are made of sulfuric acid, less beautiful, a little bit more painful. Mars actually has clouds. Mars has got a bit of a pathetic atmosphere, actually. It's very, very thin, but it does have clouds, and those are made of carbon dioxide crystals. Jupiter has those massive swirling storms, which could swallow up the Earth. Those are ammonia clouds. We've then actually got the moon, Titan. Titan is in orbit around Saturn, and it has a stable atmosphere. It's the only moon in our entire solar system with a fully stable atmosphere. And its clouds and its atmosphere is mostly made of hydrocarbons like methane and ethane. And then we've got Neptune as well, and that's also got ammonia and methane clouds. And you can see just even from these pictures, and these are very tiny snapshots of these planets, just how diverse and how different these worlds are, even though we put them into those kind of size and group categories. One of the things that I like to do is called world building. And this is a technique that is used by science fiction writers. It's used by fantasy writers. It's used by any writers, to be honest, to kind of use the fundamentals and build up what it is that we need to understand about what we're putting together so that we can make it as realistic as possible. And when I'm talking about world building, I'm literally talking about world building. What do we need to know to understand more about that planet? And we can do that by looking at our solar system, and we can do that by looking at the different things that we need to understand to make this climate system work. So I said it before, and I'm going to say it again. Planets, and especially their atmospheres, are chaotic. That's just a fundamental aspect of atmospheres. If you change a very, very small thing, that butterfly effect is true. In fact, it's the name of the first paper that was written about this. If you change a very small initial condition, the starting point, the end point can be completely different. And that's what we see when we look at planets. So the biggest questions that we've got here is, what's the star like? What kind of star are we orbiting? How far away are we from that star? Because that's actually going to define our temperature. And temperature is really important. A star is giving off this radiation. We need that. So how far away are we from that star? How big is the planet that we're talking about? How big is the world? Are we a moon? Are we a planet? How big is it will define its gravity. So it will define what it's like, define how much it can hold on to. What is its atmosphere like? And this will kind of rely on that gravity. How big is this planet will define in some ways what its atmosphere is like. But we'll see in a second that there's actually big differences for the same mass, the same size of planet. So what is its atmosphere like? What is it mainly made up of is the biggest question we're trying to find out for exoplanets. And how fast is it rotating? Now, this is obviously an exaggeration for the Earth here. It takes 24 hours for us to rotate. The rotation will define the circulation patterns in the atmosphere. So how the atmosphere, the gas, moves around that planet. And you can see that for our solar system. So the Earth has a lot of Hadley cells. Its atmosphere is rotating. Jupiter, rotating incredibly quickly in just a few hours. And you can see those banding structures. Those bands are quite literally from the rotation of the planet causing those band structures to appear. And then you've got something like Titan, which is the moon of Saturn again. Titan is what we would call a tropical planet because it's just got the one cell that goes from the equator to the pole. So the rotation rate of your planet, your moon, will define how your atmosphere acts. So these are like the biggest fundamentals we want to talk about. And if we want to go into a little bit more detail, you can also look at the tilt of that planet because that will define the seasons. So it will define how it acts over a longer time scale. So when you're building a world, when we're looking at an exoplanet, these are the questions we want to be answering. And I'm going to hopefully show you how we're doing that. From our solar system, the first thing that we need to consider is actually the fact that we're living inside two atmospheres. We're living inside the Earth's atmosphere, and the Earth is living inside the sun's atmosphere. And the sun is one of the most fundamental things we need to understand when we're looking at planetary systems. What is the star? And for our sun, we've got a gorgeous view of our primary star and lots of different telescopes up in space looking at it continuously, and ones from the ground. And this image with the multiple colors, that's from SDO, the Solar Dynamic Observatory. It's one of my favorite ones to go through and look at the pictures because you've got amazing pictures in lots of different wavelengths of the sun and its atmosphere. And sometimes that atmosphere can get a little bit violent. This is a solar storm that I studied for my master's, and you can see that the sun is ejecting plasma at high velocity towards the Earth. So this camera actually gets very pixelated at the end. The image actually stops before it completely wipes out the CCD on this camera. And this storm then resulted in me measuring the auroral substorms across the northern polar regions. So I was studying up in Svalbard in the Arctic and looking at these solar storms. So we are living inside a very dynamic atmosphere, which is also inside an atmosphere. So there's also the importance of studying the star. Like I said, our solar system really gives us an array of different types of planets. You can see here the composition of the atmosphere of these planets. And this is a really important figure. And I love this one from Compound Interest, which is a really great chemistry infographic. And what it's showing you is the main composition of the atmosphere. So the Earth has a nitrogen-based atmosphere. And then it's showing you how much of other materials are in that atmosphere. So from this, first thing that you can see is that Venus and Mars have a CO2-based atmosphere compared to the nitrogen-based atmosphere of the Earth. Now, Venus is pretty much the same radius as the Earth and pretty much the same mass as the Earth, but its atmosphere is completely different. So this is really just highlighting how the size of the planet alone does not tell you nearly enough about what that planet might be like. We can also see for the giant planets that hydrogen makes up the majority of the material in those atmospheres. That's the same for Jupiter as it is for Neptune, which is a lot smaller. It's less than half the size of Jupiter, but it's still bulk made up of hydrogen. So these are the giant planets. When you hear giant planet, we mean that it's got hydrogen mostly in its atmosphere. And then those really tiny differences that you can see. So for example, between Uranus and Neptune, Uranus has more methane in its atmosphere than Neptune does. And this difference is actually the reason why they're different colors of blue. So already that fundamental small difference between those different parts of the atmosphere and how much there is telling us something new. So understanding what an atmosphere is made of is really important for us to try and understand what that planet is like. Going to go into some pictures and some exciting parts of our solar system. Some of my favorite facts about the solar system before we head out to the exoplanets. Venus, as I've already said, is pretty much the same as the Earth, but it is, honest to God, our evil twin. It is not a nice place to be at all. The temperature at the surface is 700 or so degrees. It has essentially volcanoes all over the surface. The pressure is 90 times that here on the Earth. And that's deeper than any military submarine can actually go. So we can't go that deep. And the atmosphere that you have to get through before you get there is made of sulfuric acid, which would melt your skin. So once you get to the surface of Venus, you are quite literally going to melt, be crushed, and boiled. It's a pretty horrible place to be, but it has fascinating clouds. And if you've seen recently, there was a paper which showed that they have detected phosphine in those cloud layers. And phosphine is a really interesting material that we're still trying to understand here on the Earth in our laboratories, trying to understand how it's made and what that means. Because here on Earth, phosphine is predominantly made by life. But there are so many chemical pathways we do not understand yet that we need to try and understand where on Venus that phosphine is coming from. Mars is a favorite amongst most people for planets. I'm not a massive fan of Mars. If you've seen anything I've done before, you'll know that. That's because its atmosphere is really thin. What you're seeing on the right here is a basically global dust storm. The planet has literally covered its entire surface in dust that has been lifted up from the surface, spread around the atmosphere. That's pretty impressive. The speeds of this are technically hurricane speeds, but the air is so thin, you wouldn't even feel it. So that's the only thing that's wrong with The Martian. In fact, the author, when they found out that this wouldn't happen, those storms wouldn't be as violent as they are in the movie. If you haven't seen it, please watch it. It's amazing. Read the book. It's an even better book. When he found out that basically hurricane speed winds on Mars were pretty pathetic and you can't even fly a kite in them, he was pretty upset. So Mars on the atmosphere side is pretty pathetic, but you do get lightning storms in those dust storms. So that's kind of cool. Jupiter is, I'm probably going to vote as my favorite planet in the solar system. This image is enough to kind of go with why. You can fit 3 Earths in that storm. And the storm does keep changing size, but fundamentally it is so much bigger than our planet. And the storm evolves over time, but it has been recorded for over 300 years now on Jupiter. So that's a really long-lived hurricane. This is one of the poles of Jupiter, probably my favorite image of Jupiter, because what you're seeing there are vortices that we never even expected to exist. The solar system is all fairly much on the same plane, which means we see the planets fairly edge on. We've always seen that gorgeous banding structure of Jupiter. We've seen that storm when you look for a telescope. We haven't seen the poles until we sent spacecraft there. And this is an image of one of the poles of Jupiter, and it's completely different from what we ever expected. There are a huge number of people right now who are working in Earth and planetary science here at Bristol who are trying to work out how these vortices are formed, running numerical simulations to try and understand how they are formed and how they evolve. How deep are we looking in the atmosphere here? So there's so much that we're still trying to understand about Jupiter. And this planet, like I said, is huge. It's 11 times the size of the Earth. So it's a massive planet. And that's just the diameter. That's just the radius. You can fit 320 Earths in its mass. It's a true heavyweight of our solar system. But it doesn't rule on storms, especially polar storms. Again, we've sent satellites, we've sent spacecraft to these worlds, and this is Saturn's pole. You can see there very strangely sharp and straight edges, and you can zoom in and you can zoom in. Straight at the eye of that storm is that big vortex and all of those cloud structure. But that hexagon really threw us for a while. So nature quite likes to make hexagons. It's fairly natural shape to be in because the angles of that are really, really simple. But creating a storm that large and that regular really, really flew through us. And the Cassini images, the Cassini spacecraft, which was in orbit around Saturn for 13 years before it plunged into the atmosphere, was really instrumental in building up British science as well, because Britain had a huge part in that mission. A lot of the people working in America on that mission are actually British people as well. So we really kind of have ported it around the world. We are the solar system experts in this country. And then I'm going to finally stop at Neptune before we head out into the galaxy, because Neptune has some of the fastest winds in our solar system. Neptune's winds are 1,800 miles per hour, which is really, really very, very fast. And I can't really quite put into anything how bloody fast that is, but it's really fast. And these storms are next to invisible in the atmosphere. It looks like a fairly quiet planet. And then every now and again, you'll get these really nice little dark spots like you can see there. And these little bands of wispy white clouds. And those white clouds are made of ammonia. So we've taken a tour of our solar system. I think it's time that we kind of go to the stars and take a little bit of a look at exoplanets, planets that are beyond our sun's reach, that are orbiting other stars in the sky. And to do that, I'm going to give you a little bit of a history first, because I love a good history lesson. My father's an amateur historian, so I grew up surrounded by history books and learnt nothing, went into science instead. So I'm doing some science history for you here. Exoplanets are not a new concept in the slightest. They've been thought of for over 2,000 years. Epicurean philosophy, the ancient Greek philosopher Epicurus, actually is based around the fact that there are infinite number of atoms in the universe, and therefore there must be an infinite number of everything, so an infinite number of worlds. And he really kind of pushed forward this philosophy of the plurality of worlds, so that there is planets both like and unlike our own. So this guy was, a contemporary of Aristotle who completely screwed up our view of the universe by sticking the Earth at the center. There was a fight, a balance between those. But the idea that planets can exist has always been out there. It's always been part of the way we think. And one of the striking things, actually, now, if we look at astrobiology, if we look at the fact that we're trying to understand how life can evolve in different places in very extreme environments, they never, ever had a problem with life being possible on Mars, on the Moon, on Saturn, on Jupiter. But they had a problem with other planets existing beyond our solar system. So it's kind of baffling to me to be so open-minded and yet have walls that are built up there. So it actually took until the 1600s, 2000 years later, before people started going, oh, you know what, there might be planets around other stars. We should probably look for those at some point. And that was some work that was put forward by Christian Huygens. He's a Dutch astronomer, and actually the lander that landed on Titan from the Cassini mission was named after him. And he postulated that because we can see with our telescopes, and we can see actually with the naked eye sometimes the moons of Jupiter orbiting Jupiter, so we can see those pinpricks of light. He said that because we can see that system, we should be able to see that around other stars as well. Now, the problem with this idea is that to do that measurement, those planets need to be really bright and they need to compete with their star's light. And at the time, they genuinely didn't have any idea how far away the stars were. They had no idea that they're so far away that the brightness of those planets would have to be immense. So this was something that really wasn't plausible or possible to do. It was then a couple of 100 years after that the first false detection of an exoplanet was made. So this was done in the Madras Observatory in India by W.S. Jacob. And he did a lot of studies of binary stars and measured the motion, the position of binary stars on the sky. And he noticed this star, 70 Ophiuchi, which is already a binary, he knew it was a binary system, was actually moving. And this movement didn't quite match with what was expected. So he said, and he presented this scientific paper to the Royal Society, he said, I have discovered a planet in orbit around 70 Ophiuchi. It was an amazing, ridiculous thing to have happened because no one had been able to measure things so accurately before. But it turns out that what was being measured was actually a third star, and that system is actually not host to an exoplanet. So that's why we called it the first false detection of an exoplanet. Exoplanet was claimed to exist and it was not there. So it is a false detection. So we've gone from, back in ancient Greece all the way up to essentially modern astronomy with observatories and making measurements of the position of stars. So exoplanets have a huge, huge history, but it really wasn't until the 90s that planets became a reality outside of our solar system with the detection of 2 small worlds around a pulsar. And then it wasn't even until 1995 that the first planets were detected around a star like our sun. And since then, we've had a huge number of worlds. Now, this plot might be confusing, but what you're seeing along the bottom is their distance from their star. And along the side is the mass of that planet in Jupiter's. So we can put on our solar system there. And you can see that a lot of the worlds that we're finding are very different from our solar system in terms of how far away they are from their star. They're very, very close to their star. They're also mostly quite big. They're mostly Neptunes. So Neptunes are the most prominent, the most abundant planet in our galaxy that we know of. But then we've got this big cluster of these giant planets. So to try and imagine what these are like, I want you to think the Earth is the size of a pea on this scale. If you go to Jupiter, we're talking about something that is the size Oh, sorry, we're not going to Jupiter. We're going to Neptune. Neptune is about the size of a plum. So a nice little red plum. And then Jupiter is the size of an orange. So you can see here on this scale just how large Jupiter is. And then some of these planets, you can see they extend well above Jupiter. They're up to, you know, beautiful spherical watermelon size or pumpkin size worlds. These are very, very large worlds, but you can see they're so much closer to their stars. Actually, in some cases, they're 20 times closer to their stars than we are to the sun. Imagine sticking Jupiter 8 times closer than Mercury is. It would look ridiculous in the night sky, absolutely ridiculous in the daytime sky. So these planets are quite literally speak to that title that I've given you, stranger than fiction. They'd never, ever been imagined before. In fact, the first detections of them were completely discounted. And it wasn't until 1995 when the first one was like, no, we found an exoplanet. Here's the measurements of it, that everyone went, oh, hang on, let's go back and look at some of these other things that we found. Oh crap, they're exoplanets too. Like, this is crazy. We never expected it. Like, our human imagination was limited. And what this has just shown us is that nature's imagination is just vast and we don't even have a chance of understanding it. So we just got to keep looking for these things to try and really build up that picture. And I'm going to really focus in on some of these worlds, and most of them are going to be in that clump, which is Jupiter-sized and very close to the star. They're called hot Jupiters. And the reason I'm going to focus on those worlds is because they're much, much easier for us to measure. So you can see in this picture, on the left is the same picture that we saw before. But what I've done now is I've removed all of the planets where we only have a small amount of information about them. So I've removed all the planets where we only know the mass of the planet and we don't know the size of the planet. And I've removed all of the planets where we know the size of the planet, but we don't know its mass. So all of these worlds that you're seeing here, roughly 300 to 500 of them right now, we know the mass of them, we know the radius of them, and therefore, if you look on the right side, we can plot out the density of these worlds. So from the density, we can start to try and understand what they might be like. We can start to pick apart, okay, if we put that in the context of the solar system, it actually fits a lot better. We've gone from this really alien landscape where none of the solar system planets remotely look like these worlds, to putting them into a density space of their mass and their radius. And we start to go, oh, those look like some of our solar system planets. What does that mean? What can we understand about that? And you can see here, I've put on some solid lines there. Those are models. Those are models which you would expect if you had constant common density. So we've got our Earth-like rocky planet. This is essentially mostly magnesium silicates, which is most of the rock that we've got here on Earth. It's common sand, basically. We've then got pure iron. And you can see Mercury fits on that line pretty well. Mercury has an incredibly large core compared to its size. And we think that that's due to different things happening in its formation. We then got this cold hydrogen line. This cold hydrogen line clips right through Saturn and Jupiter. And this is saying that these planets are mostly made up of cold hydrogen. This is the density profile of that cold hydrogen with mass. So you can see the clump that we've got there really up by those Jupiters, and they're much, much larger than that in most cases. They're those watermelon size compared to those oranges. And that's because they're incredibly close to their star. They're being inflated somehow. Their density is much, much lower than Jupiter's because, and even Saturn can float in a bathtub. These things are much lighter than that. They're lighter than styrofoam, some of them. They're puffy, puffy planets with very extended atmosphere, very large radii compared to their mass. So these super puffs, as we call them, have been really important for us to try and understand their atmospheres. But it's that gap in between where you're seeing Uranus and Neptune, where we're completely stuck right now. We've been at this for 20 years. We've been looking at their atmospheres for about 10. We've got no idea what's happening there. And that's the biggest question that we have right now in exoplanet science is what happens to an atmosphere to go from that cold hydrogen dominated world to those Earth-like terrestrial worlds. So we call them terrestrial worlds. We don't mean they look like Earth. We mean that they are rocky. They are dominated in mass by rock content rather than their atmosphere. So Neptune is dominated by a hydrogen atmosphere. We don't think it has a surface. The Earth and Venus are dominated by their rock content. So there's a transition in there somewhere from terrestrial rocky to gas giant. And then from gas giant to our Jupiters. And we're trying to understand a lot more about where that is. And like I said, most of the planets that have been discovered are in this range between our Jupiters and our terrestrials. And there's so much we need to understand about our own solar system planets there. We haven't had a mission to Neptune since I was born. We need a new mission to those. So the idea is to send a mission to those within the next decade to try and understand them. Now, I said send a mission to them. That would be the starting point. It would then take a further decade to get there. So in a couple of decades, hopefully we'll learn a little bit more about our ice giants, and we can fill in this profile for our own solar system, and hopefully also start using the exoplanets in the ways that I'm going to show you to understand them in reverse. By looking outwards, we can look in at our own planets. Put the scale on there as well, so you can see what it looks like in that density profile. So now I'm going to kind of jump to some of the science of what I do, which is looking at the spectra of these planets to try and understand what their atmospheres are made of. And I do this with things called transiting exoplanets. And transiting exoplanets are planets that are oriented such that the planet literally passes in front of the star from our point of view. So if we've got our star here, we've got our planet, it's passing in front of the star. It's blocking out some of that light. And by blocking out some of that light, we can measure it. So you can see on the left-hand side there, you can see that line, that's called a light curve. And from that, we're taking a picture every minute or so. We can see where the planet passes in front of the star, it blocks out some of that light on the order of 1 to 2% of the light. And then when it's finished, when it's gone out of the star's disk, the star then becomes bright again. So we're able to measure these transiting planets. And from that, we can actually use spectra to understand what they're made of. So every atom, every molecule in the universe absorbs energy, absorbs light in different ways. And what we can do is we can look for the way that the light is being absorbed and blocked by the planet and its atmosphere, and try and understand what the atmosphere is made of. So what you're seeing here is how we can get a continuous spectrum of the star. So we can get a spectrum of the star so we can see what the star is made up of. When the planet is then passing in front of the star, we can get an absorption spectrum, because some of the light's going to go through the atmosphere before it reaches our telescopes. And I'll show you in a little bit more detail what that looks like. So from that, we can measure what's in the atmosphere of the planet. And then actually, I'm showing you in this graphic here on the left, as that planet passes behind the star again, you see another tiny dip. This is a very small dip. And you can't see it for all planets, because what we're measuring there is light coming directly from the planet, either reflected from the planet's clouds, or it's coming from deep within the planet where it's still kind of hot from formation. So we can also measure the light directly from the planet. But I'm going to focus on this light that we see when it's in front of the star, when it's transiting in front of the star. What I'm going to show you here is how that happens. So we're looking at this world. It's got an atmosphere around it. Some of the starlight actually passes through that planet's atmosphere, gets scattered, gets moved around by the atoms and molecules in that atmosphere, and then it comes out and then it reaches our telescopes. And what we're measuring is the spectrum of that atmosphere. And it will look a little bit different if you've dealt with spectra before, if you've dealt with absorption before. So you've looked at a sodium lamp maybe in the lab, or you've looked at a street lamp with a grating or something, then you'll know what a spectrum looks like. And what we're doing is we're measuring the transit depth, is what this is known as. And we're measuring that change in light from the star. And that change in light will be larger if there's something in the atmosphere that is blocking that light, that is absorbing that light. So I'm going to show it to you in a number of different waves. So we're looking at the wavelength. If we want to look at this in blue, so if we look in the blue color, the size of the planet will look different. If we then look in lots of different colors, we can start to build up an understanding of what that planet looks like, how big that planet is, how much light it's blocking, physically blocking from that star in lots of different colors. And because we know that each atom and molecule absorbs light in different ways, we can use what we know about different molecules and how they absorb light and build up a picture of what might be happening in this planetary atmosphere. So here, we've built up a picture of that atmosphere. The atmosphere itself is composed of it's mostly hydrogen and helium, but it's got some sodium in it, and it's got some potassium in it. And this sodium and this potassium absorb the light, so they block the light at very specific wavelengths. So if we look in those wavelengths and we see that the planet appears to be bigger, it's blocking more light than it did before, then we can say that there's sodium in that planet's atmosphere. So what you're seeing here from this just quick diagram is that those different elements in the atmosphere will change how much light is blocked. And from that, we can work out what's in that atmosphere. So this is inverted from what you might see in the lab. In the lab, an absorption spectrum would typically be a dip because the light dims. Because we're measuring an effective area of the star, so we're measuring the area of the planet relative to the area of the star. Because we're measuring an area, if something is absorbing, it will block more area because it's absorbing that light. So we'll see a spike, we'll see it get bigger. So if you're thinking about lab spectra, flip that over, and that's what we're measuring for exoplanet atmospheres. And here is an example of an exoplanet spectrum that has been measured. So what you're seeing here, and I've labeled some of them for you, you're seeing that sodium, you're seeing that potassium, but you're also seeing those bumps and those wiggles. They've really broad features of water in the atmosphere. And this is water vapor. So this is gas. So water in its gas form. Water is the third most stable molecule in the entire universe. No matter where you look in the universe, you'll find some aspect of water there. It is happy to be frozen. It is happy to be a liquid. It is happy to be a gas. The only places you won't find it is when it's so hot that the water, the hydrogen and the oxygen are like, we don't want to be friends anymore. So in all of the places in the universe, you're going to see water. And what we're seeing here is water vapor in the atmospheres of these giant planets. And that's really exciting. So trying to explain in a slightly different way what we're seeing, this is going to physically show you what we would measure in terms of the size of the planet with these different features. So look at the size of that planet. So the size of the planet increases when there's something in the atmosphere to block that light. And that's what we're physically measuring, is that size of the planet changing because there's something in the atmosphere absorbing, blocking that light. And we've done this for lots of different worlds, nearly 50 worlds now. And I've been involved with these since I started my PhD. And what you're seeing here is the main figure from my PhD thesis. I actually did the analysis on a lot of this, and then I actually made all the figures for this paper as well. And what you're seeing is 10 giant planets. These are Jupiter-sized worlds. You can see them spinning very, very slowly in the left-hand picture. These Jupiter-sized worlds have sodium in the atmosphere. They have potassium. They have these beautiful water features in the atmosphere. But what we found, like our solar system, they're all different. Every single one of these worlds is around the size of Jupiter. Every single one of these worlds is very close to their star. There are, 1,000 to 2,000 degrees. They're very, very hot, but they're all pretty much the same if you group them in phase space. But they were all different when we looked at them. And we had to start to understand how these very small changes that I talked about at the beginning can have an effect on what that planet's like. And what you're seeing here is we've ordered those planets from what we call clear. So we're seeing these beautiful atomic features, we're seeing these molecular features, down to these cloudy ones where we're not able to measure as much as we thought we would. And what we did from this is we used this as a predictive tool to try and understand what we can go and look after. How can we use this to predict what we should be seeing given our new understanding? So we went in with an understanding, we measured it, and we were like, oh, that's different. Okay, well, let's reevaluate. What do we think is going to happen now? So we went back in and we looked at some of these worlds and we tried to understand them more. And what we've done is we've looked at a ton of worlds, and I can just put them all on top of here. We've looked at worlds from these giant planets all the way down to terrestrial worlds. These are rocky planets that we're looking at. We're trying to understand their atmospheres. And we've done this for, I mean, all of these images that you're seeing here is the last 10 years. It's insane. We've gone from discovering that planets exist beyond our solar system in 1995 is when we first got the opportunity to really look at this. In 2000, the first transiting planet was discovered. And now we're starting to measure the nature of these worlds and trying to understand what they're like. We've looked at roughly 50 of them with the Hubble Space Telescope, and we have a huge number planned to look at with the James Webb Space Telescope. And this number is increasing every single year. And it's really, really great to be able to work with Hubble data. And I've talked to you already about this beautiful water absorption feature. We've actually discovered water vapor in 80% of these planetary atmospheres. So I said that it's a really common molecule. We expect it to be there. This isn't a surprise. But what's amazing is that we've been able to measure it. If we go looking for it, it's there. So some of our predictions are really right. We know what we're talking about. And we can use those predictions. We can use our understanding of physics and chemistry to work out what we expect to see. So what we're seeing is this is the expectation. This is a model that has been created from a radiative transfer simulation. So we're basically tracing where a photon goes through an atmosphere. If it hits something, something happens to it. And then we work out what that might look like. So what you're seeing here is what we expect to measure if we point our telescope at this transiting planet. But what we actually saw were a few different things. We saw one situation where we weren't measuring exactly what we expected. We were measuring water absorption features, which were tiny compared to what we expected. And then we were measuring things in the optical where it was scattering like crazy. The light was being bounced around like nothing else. So our atmosphere has very small particles in it and it scatters all the light around. That's why our sky is blue. We were seeing with these planets that their atmospheres were scattering light in all different directions, which suggested that they had very, very tiny particles in their atmosphere. So this was really, really baffling for us. And what we were able to show with a large study that I led was that we're measuring water absorption features, not at what we expected, but much, much smaller. And this told us that there's something in those atmospheres that's getting in the way and interacting with the light. And what that stuff is one of my favorite things to study. And that is clouds. And the reason why I'm really excited by these clouds is because they're nothing like what you might expect from our solar system. They're not made of water. It's too hot for water to turn into a liquid. These temperatures you can see on here go from 700 to 2000 Kelvin. These clouds are made of gems and jewels and liquid glass. So that main cloud, those silicates, those green ones, that's liquid glass. Those aluminium oxides, those salts are quite literally table salt. We've then got sulfur-based materials. We've got that glass, that enstatite, that forsterite, magnesium silicate materials that form the majority of Earth's crust. And then we go up to these really hot planets where you've got aluminium oxides called corundum, which is the basis of rubies and sapphires. The clouds in these atmospheres, those scattering features, are made up of gems and jewels. So not the only reason why I love clouds. I love clouds because they're dynamic and interesting, but it's geology melted and stuck into an atmosphere. So there's nothing stranger than that. And if we can put that on the diagram, if we use our models to try and understand this, we can go from something called Rayleigh regime, so where we're scattering light, to the Mie regime, which is where the wavelength of the light matches the wavelength of the particle, until we get to, the geometric optic regime, which is causes our rainbows and things. if we look at these particles, we can model what those clouds might do to an atmosphere. And what we can start to see is, how can we test this? How can we test this hypothesis that these clouds are made of these ridiculous materials? And one of the things that I'm looking forward to doing in my time here at Bristol and in the coming years is actually testing this hypothesis and measuring those features of those clouds. So what you're seeing there is what we should be measuring. We should be able to see if these clouds are indeed made of liquid glass in the atmospheres of these planets. So that's the physics behind it. That's the bit I think you can probably tell why I'm so excited about those. But where's the fun part? Where's the interesting human story? So we're going to just explore a few of these before I end. I know I'm going over time, but I'm just going to quickly take you through some of the exciting things that you can do with this information. So one of the things that you can do that I enjoy doing is turning these into sunsets and trying to understand what that means if you were looking at it with your eyes. So the color of the sunset can really tell you a huge amount about these planetary atmospheres. And this is a beautiful sunset. I think you will all agree. But that's actually the sunset if you look at our sun from the Earth. What you're seeing here is the equivalent scale sunset on one of these alien planets. This is a planet called HD 189733b, and what you're seeing there is actually the size the star would be in the sky, because we're so much closer to it. So you'd see all of these colors all at once. And the sunset is actually very similar to our sunsets because the atmosphere is scattering the light in a very similar way to the Earth's atmosphere scattering the light. So you'd see this nice deep red sunset. So you can see from that, we've got this big scattering slope, and that scattering means that you're preferentially scattering away in the blue, so you end up with this beautiful red sunset. This planet's actually really weird. It's a beautiful blue color, but it's also around an active star. So like I said, we're in the star's atmosphere. Here at the Earth, we're in the star's atmosphere, 1 AU away from the sun. This planet is much closer to the sun. It is 20 times closer to the sun than we are. And the star is bombarding it with radiation. And what you're seeing in that video is an artist's simulation of the atmosphere being literally blown away from that planet because the star is actually just bombarding it with radiation. Now, the next one is my favorite one. This is what I call the film noir planet. It's a nice gray scale with a little bit of grayscale thrown in there. And this planet is really fascinating because it's an incredibly hot world. It's over 2000 degrees. But what we've been able to measure from its spectrum is that it's scattering light at so many different wavelengths in so many different ways. And from that and from its temperature, we can combine this information to try and understand, okay, what is in the atmosphere that's scattering the light? A gas shouldn't be able to do this. So what is in the atmosphere is very likely to be clouds of those beautiful corundums, those rubies and sapphires. So this planet's atmosphere has probably got clouds that are made up of the base particles of gems that we have here on Earth. And then finally, another one that just a little bit alien twist to this. This is the sunset on a planet called HD 209458b. And it's that very alien green-blue sunset. And that's because in this atmosphere, we've detected sodium absorption. So sodium lamps, if you've seen them, I'm sure you have, they glow in orange. Sodium absorbs basically all of that nice orange part of the spectrum. If you remove that from the spectrum of the star, if you remove that sodium, then what you're going to see is all of the rest of the light left. And if you pass that through the way that our eyes detect color, you end up with this beautiful blue-green sunset. So if we were in a nice balloon in the atmosphere of this planet, it's not a nice place to go. You wouldn't actually want to go there. You certainly couldn't breathe in these worlds. They don't have surfaces. But if we were going to go in a spacecraft in these planets and look through the atmosphere at the star, we'd see this gorgeous blue-green sunset. And we've measured the atmospheres of so many different worlds. We're still trying to understand what the nature of these worlds are like. We're world building. we're taking all of those questions I had and filling in the blanks, trying to understand what are these planets like and what does that mean for those worlds. So I'm going to leave it there by saying that I have a podcast called Exocast where we talk about everything to do with exoplanets. If you're on Twitter, we run a knockout competition between exoplanets to find the best exoplanet of the year. So keep an eye out for that because that's coming in the next month or so. And if you like Twitter-based competitions, then it can get quite heated. Astronomers and exoplanet scientists tend to share a lot of things about the planets. But for that, I'm just going to leave it there and answer as many questions as I possibly can.
Well, thank you so much, Hannah. Guys, quickly fill up the chat. I bet you've got loads and loads of questions. Oh, here we go, here we go.
What is my favorite fictional planet? Damn, wasn't expecting that one. I can give you my favorite planet, fictional planet. I'm going to think about that whilst I'm answering the rest of the questions. Fictional.
Well, okay. I've got a quick question. I was just wondering if it was possible, if a planet were to be shifted from its orbit, could it change its state? So go from one of those cold hydrogen planets to a more rocky planet?
That is a fantastic question. And that's actually what we're seeing with some of these worlds. So there are some planets which are just big enough to have these hydrogen helium envelopes like Neptune. So actually, if you took Neptune and you put it right next to the sun, over time, the sun would probably give that planet's atmosphere enough energy. It would bombard it with enough energy that the hydrogen in the atmosphere would be escaping from that atmosphere. So over time, you can imagine that that planet could lose all of its hydrogen atmosphere. And if Neptune lost all of its hydrogen atmosphere, what would be left is whatever the core is made out of. So for some of the planets that we've been seeing, actually, we're measuring them actively losing their atmosphere. So you saw that video of HD 189, that red sunset planet. It's losing its atmosphere. Now it's too big. It's as big as Jupiter. So even if it kept doing that for another million, billion, tens of billions of years, it wouldn't lose enough atmosphere. But if you've got a small enough planet that's losing this atmosphere, then it could end up like a rocky planet in the end. So it's all of its atmosphere has been stripped away. And we're actually seeing that occurring in some of these worlds. That was a fantastic question.
Oh, thank you though. Oh, we've got another one.
Can you tell the age of exoplanets? So that's a really tough question. We can tell the age of stars, which is very helpful. And we can only just about do that for some types of stars. For most of the planets that I've been talking about, and for most of the planets that you'll probably hear about, they're fairly old. They're essentially what we would call established solar systems. They're not changing rapidly. But we do have some very young planetary systems. So the planets that you can get a direct image of, so when you mask out the star and you can see the planets glowing, like Christian Huygens suggested you do, like you do with Jupiter's moons, if you can see those ones, those are normally in very, very young systems. And that's because they're still very hot from formation. So they're glowing, they're still glowing. So we can actually measure that if we block out the star's light. So those are generally very young systems. And then when we're talking about transiting systems, they're very, very, old or middle-aged systems. So we can tell from the star, but what we're, understanding the dynamical history of that planetary system, how did it get to where it is now? The Jupiters didn't form there. They had to have come in somehow. So that is really left to numerical simulations. And one of our researchers here at Bristol, Zoe Leinhart, runs these numerical simulations to try and understand how we can form these worlds. How did they get there? How old are they? How dynamic was their formation? Did things hit them and cause them to completely change? So we have some great researchers here at Bristol that are doing things like that. So if you're interested, go check those out. I still can't think of my favorite planet. I'm a Stargate person. I don't know if any of you are old enough for Stargate, but my computer's called Abydos, if that helps. So I'll go with Abydos for now. Maybe Chulak because it's got 5 stars, which is really cool. 5 stars in the sky would be pretty awesome. Do I have a favorite star or planet in the galaxy? I don't know that star. That's awesome. I'm going to look that one up. My favorite star, my favorite planet is a planet called WASP-17. It is a giant planet. It is incredibly large compared to its mass. So it's really, really light, really light. I could probably, you know, if I was a giant, pick it up. And I love that planet because it's actually traveling in the wrong direction around its star. So I was saying that we're trying to understand how these planets evolved, what happened to them in their lifetime. This planet, clearly something happened because it's traveling in the wrong direction entirely around its star. So something crazy happened to this planet to make it travel backwards, and we don't quite actually know why. Do you think the exoplanets we can currently detect are representative of what all exoplanets are like? Another great question. So one of the ways that we're trying to understand this is with survey missions, statistical missions. And the best one that we have right now is called the Kepler Space Telescope. That ended it was launched in 2009, and it ended its first primary mission in 2013. And what it did was it pointed and stared at exactly the same part of the sky for 3 years solid. And during that time, what it was able to do was to look at all of the stars in its field of view and it go, okay, let me count how many planets there are. And by counting how many planets there were, we're able to kind of take that number and get a statistic on what we call the occurrence rate. How often do these worlds occur? Which is how we can actually say that a majority of stars actually have planets that are smaller than Neptune, but larger than the Earth. The majority of worlds in our galaxy are nothing like we have in our solar system. We don't have a planet that represents that population. And most stars have one of these worlds. So we've learned a huge amount by looking at other stars and getting the statistics. But one of the things that we're trying to understand is the statistics of all planets, which is much, much harder to do. And all of the observational techniques we use to detect these planets all have their own biases. They're all really bad at some things and really good at other things. So we're trying to still understand how those overlap. Isopolar storms of large gas giants such as Jupiter, Saturn, in the very poles, do the wind speeds slow down, such as the eyes of hurricanes? That's another good question. And when you're modeling vortices, so you can model vortices as essentially a fluid is what we're modeling these as. And you can work out how those speeds have to change as you go in to maintain the angular momentum. So how fast these are spinning, what the speeds are, the velocities of these. So at the middle, you would expect them to be much, much calmer. So that might then be an eye right the way down to see deeper in the atmosphere, like we would if you're taking a picture of a hurricane from the International Space Station, the eye of the storm. You might be able to see some of the ocean through that eye, whereas the rest would be shrouded by the cloud. So we think that if we're looking down the center of these vortices, we're seeing deeper into the planetary atmosphere. And from that, if we can measure the spectrum of that atmosphere compared to the clouds, which are going to be much, much higher forming those vortices, we can get an idea of how the profile of the atmosphere changes with depth.
Okay.
Yes, to being old enough.
It seems like we don't have any more questions. Oh, yeah. Wow. Thank you so much, Hannah. It's been incredible. And thank you for answering my question as well.
Not a problem. I always love questions.
Oh, well, I'm sorry that that everyone else is muted, because I think a round of applause would be in order right now. But yeah, I'll give you a little clap.
We've just actually had one more question from Stefan. He asked, can part of the atmosphere expelled from a planet come to another close one?
So it depends on how that's expelled, but we do have something in our solar system called planetary mass transfer that we know exists because we have found meteorites on the Earth which are from Mars. So something's impacted Mars. Meteorites the rocks have broken off. They've landed on the Earth after probably passing around the solar system a few 100,000 times. So we know that there is mass transfer between different planets. Now, it depends on what the density of that atmosphere. If you're blowing off an atmosphere, the density of that gas is going to spread out and spread out. Whereas rocks are clumps of material that stay together. The gas will spread out and spread out. So the amount of it that reaches another planet or hits the star will be very, very small and very difficult to detect.
Okay. Is that another question you've got there?
Would it be possible to hypothetically have atmospheric based bases in these poles? You'd need something to suspend it. The atmospheres of Jupiter, for example, is very cold. It's not a nice place to be. It's a very cold place. The density of the material changes quite rapidly as you go from the different stripes. So the different stripes actually represent thousands of kilometers difference in height that we're seeing. So essentially cliff edges of clouds. So it would really, really need to be something incredibly stable. And because the atmospheres are moving so much, it would be very difficult to do.
Okay then. Okay. Oh, thank you so much. Oh, yes. Okay. I thought another question's going to pop up. No.
All right.
Well, and thank you everyone for coming. I hope you'll come to a lot more fantastic chaos events and more talks. So yes, hope you enjoy your evening. And thank you again, Hannah.
Bye, everybody.